I want to share you this example. There are one dependent variable, 8 independent variable. Time, potential, advertisement expenditure, and market share. And for last year's market share change, the count, how many customers you have, how much work, loading, and what's the rating from your supervisor. Can you see the scale is different? Okay. You can see the scale is different. For the dependent variable, there are 4 digital. For time, how long have you worked in this industry? Maximum is 3 integer. And the potential, market potential, like in India, okay, there are so many customers. So the market share is very huge. And like country in Indonesia, there are 300 million people. Okay, so the market or the market potential is very huge. The country like Taiwan, only 23 million people. South Korea, 50 million people. In Vietnam, there are probably just near probably 90 million people, almost 100 million. The more consumer, the potential of the market is bigger. And you can see the integer, there are 4 and 5. Okay, 5. The advertisement expenditure, and it's 4 integer. Maybe this is million US dollar. Market share is 2 integer, and this is just 1 integer. The smaller integer, the bigger the coefficient for unstandardized. Okay, and before we run the regression, I want to show you the correlation. Okay. Tell me which one is, this is Y, which one has the highest correlation with the Y? Account. The order of the importance of the independent variable is account, number 1. This is highest one. The second one is time. Okay, it thinks the coefficient is 0.623, but the correlation between time and the account is very high. So these two variables has a high correlation between these two variables because their correlation coefficient is bigger than 0.7. The third one will be potential. The fourth one will be the advertisement expenditure. This one. ADV. Okay. The market share and market share change. This one is higher. The change. Market share change. And the market share is number 6. And the other two is not big. The correlation. These two not so big. The rating will be number 7. The row, the work row will be 8. So let's run the equation. If we put all the independent variable in the model, analyze equation, the dependent variable will be cell, and we have 8 independent variable. Remember, when there are more than one independent variable, you should check the conveniently. Okay. And then we use the enter. Okay, there are forward, backward, remove, stepwise. We check the enter first. You can see we have 8 independent variable in the model. The R square is 0. I will say 92.2. Okay. The F test is significant. The T test. Okay, there are some problems about convenience between these independent variables. Okay. But I'm not I do not concern at this moment. I will check which one is not the p value has the highest one, this one. So we delete this variable, rating. So you can see the rating is number 7. Because this is the highest one, but work has the lowest correlation with the y, but since the p value, this one is the highest one, so we will delete the rating first. So I just do it manual, okay. So take the rating away from the model, run it again. Now the R square from 92% reduced to, it's okay. Even we delete one variable, but the R square remain the same. Okay, the T test we will delete the rate work. Okay, so we will delete work. R square reduced from 92.2 to 90, and the F test is significant. The T test, okay, the account. We say account has the high correlation between account and the y, but now, based on the p value, we should eliminate the count. Even this variable is so important, but based on the data result, we need to delete it. Unfortunately. And after we delete so the R square from 92% to 91.5%, and you can delete the change because the p value is bigger than 0.05. Okay, so you can delete it. R squared become less than 90%, become 89.6%. The t test, everything is okay. And there is no collinear problem between these 4 independent variables. So the model, this is the final model. And the R squared is, I will say, R squared is 89.6%. Take this 4. Eliminate this. Okay. This is the first. If I do it manually. Okay, previous. If I do it automatically, I put these 4 variables back in the model, and by using the backward, here, backward, you see what's happened. The software tell you, okay, at the beginning, the model 1, this 8 variable is in the model. The first one eliminate from the model is rating, just like we do it manual. Okay, rating first. Then the second one is row and account. And when I did the manual, I delete the change because the p-value is 0.053. But here they didn't delete. So at the beginning, the model 1, you have all 8 independent variables. You can see the p-value, and then you delete the rating. The second model, delete after you delete the rating, the warp, that's the highest p-value, is this column here, delete it. Then after delete the warp, then you, since the account that's the highest p-value, this one. P-value is this column. So the p-value is, okay, this is not significant. And this is not significant, so we delete this one. Then after that, the software doesn't delete the change, but I did. And in this model, they use backward. You got almost the same result, like the R square from 92.2%. Okay, so the second model, R square is include this file, okay, change in the model. Okay, if I use the forward, what happened? If I do it manual, okay, if I do it manual, okay. Take all the variable away from the model. Which one I'm going to put in the model? This one, account. Because the coefficient has the highest one. Okay, since there are only one independent variable, we don't need this. Okay. The R square is only 58%. The t-test is significant. Okay, which one are you going to put in? Based on the correlation, the time is the highest, the second highest one. Okay, so UA time in the model. Okay, and since there are two independent variables, we need to check the convenience between these two independent variables. And we use enter. We use enter. So the R square become 57.5. T-test, these two. Okay, there is problem. Okay. Convenient. So, and the coefficient for heat time becomes small. So actually you should not include the time because the coefficient between time and the account is very high. Yes, it's very high. So it's not a good idea to put the time in the model because there is a high correlation between time and the account. And which one are you going to put? Potential, because the height is the highest one. The third highest one, potential. We put here, and the community here, we give it a community. And the Oscar becomes 64.1. T-test. Yeah, the community is not it's not a concern. But the p-value here is significant. But if you see the unstandardized, because potential have a 5 digital, so that's why I mentioned the potential there are 5 digital, so the coefficient will become smaller. Okay. So you can check the standardized coefficient because you can see which one is more important. And the fourth one you are going to put add in the model is number 4 is advertisement. Okay. Oscar become increase a lot, 82%. The t-test, okay, and there is no continuity problem between these 3, and each one of them are significant. Okay, if I put one more in the model, which one? Number 5 is change. And again, Oscar become a little bit high because previous one is 82.8. Now it become 83.3. And the t-test here, change is not significant. So this change should not in the model. It cannot in the model. So delete. Change. Do it again. Maintain the original one, 82.8. So I will put market share in the model. Oscar become 90%, and everyone is significant, and the community problem is not concerned. Which one are you going to create? We have already put 6 of them, and which one? The rating, and rating won't be okay. You can try. I do it manually, let you see. Rating is not good because R squared doesn't change too much. It doesn't increase too much, just 0.01. And it's not significant, so you stop. So the model should be delete rating. Okay, delete and okay. So this is the final model for. We add one more. We call this forward. So I can do it automatically for you. So I do it manual first, and I'm going to. Okay, I put all of them in the model, and I use forward, one by one in the model. You can see. Okay, there. This is a sequence in the model. First one is account, second one is not this one, because there is high correlation between time and the account. But not potential, but the number 4, the advertisement, and potential, and the market share, not change. And this is the forward. And the last square, eventually, is 90%. This backward. The variable is different, and this is better. The R square for forward. Backward is all variable in the model, then take one by one. Forward, put one more in the model. Okay, so if I run the regression, run the stepwise regression. If I use the stepwise, you got the same result. For independent variable in the model. The R square is the same. Which one are you going to? Choose this one, backward. And what's the difference between these two? They look like the same. These two models look like the same. Okay. For forward, you can see forward. The difference between forward and the stepwise. The first time we put the count in the model, we check the p-value. The second time, we add one more variable in the model. If the forward, we don't check the p-value immediately. Actually, but even it's not scanned, it's still put in the model. But the stepwise, we check every time. Whenever we have a new variable, we check the older one. So for example, the model 2, we check the count again, check the p-value for stepwise. Forward, once the variable in the model, you never check, delete it. Okay. Just like people working for the government. Okay. If you don't make a big mistake, you will keep your job. But so I will always say, forward just like you work for the government, like in China or in Taiwan, or in maybe the country like it's not a sole democracy. Okay, once you work for the government, you stay there everywhere, for the rest of your life. But stepwise, like you work for a private company. Okay. You have this job this year, but it's no guarantee for you have a job again. So it's very competitive. So the difference between stepwise and forward, you can think. The forward just like you work for the government. The stepwise you work for the private company. Okay, it's very competitive. So for the stepwise, every time when we have a new variable coming, the old variable is checked whether it's significant or not. Okay. And since I have some more time, okay, I will share with you about this data. This data is Tyler. Okay, Tyler. This is my favorite example. Okay. Tyler. Here. This variable, this data is very interesting. Okay. This is the cell, the Y, the dependent variable. This is the price. This is the advertisement. There are two independent variables, and it seems to they are numerical data. Okay, they are numerical data, but you can change them as a nominal data. Then it becomes ANOVA, two-way ANOVA. Okay, two-way ANOVA. You say, how come 2.5, 2.0, 3. Okay. So you can have a data look like, I will show you. The cross table, the price, is in column. The advertisement in row, you can see. Okay. Two-way ANOVA, and the observation is 4. Okay, total there are 24. Okay. I'm going to conduct two-way ANOVA. Analyze linear model ANOVA. This is dependent variable. These two are independent variable because they are numerical quantitative data, qualitative data. Two-way ANOVA model for factorial. And I will plot price, okay, horizontal, advertisement is separate, and I will see their average. Since it's significant, I don't care about the main effect, I just look at the average for the interaction. So I don't need to check the homogeneous. This is for only, there is no interaction effect. Then you check the main effect for the post hoc test. So in this case, we sense the interaction. I know the result, so okay. So that's what I did. First, I will run ANOVA, two-way ANOVA. You can see the interaction is significant. So in this case, when the interaction is significant, we won't study the main effect for the post hoc test. Okay, we won't study the post hoc test for the main effect. We don't care about the price, different advertising. Okay, and you can see the interaction. When the price is $2, and you spend so much money for advertisement, 100,000 US dollars. The difference between 500,000 and the 50,000 advertisement, the sale, this is dependent variable. That's it. This big, probably just 300,000 US dollars. When you increase your price to 2.5 US dollars, the unit price, the difference between 100,000 US dollars and the 50,000 US dollars, the sale is reduced. When the price raise up to $3, even you spend so much money for advertising, nobody care about it. They won't, consumer, they don't buy your product. Your sale, the sale between 100,000 and the 50,000 is not much. So when the price is low, much lower, it's a good idea for you to spend more money for advertisement. Okay, this is two-way ANOVA, okay, interaction. And then you can see for the average, you can see this is the average, the price. Right. So the higher price will be for the lowest price. The higher sale will be located in the unit price is $2, and you spend 100,000 US dollars. You can increase a lot for your sales. Okay, this is two-way ANOVA. What I'm going to do, the regression. Wow. So I change this variable to scale data. Okay, scale data. Now I'm going to use regression. So analyze correlation. Always run the correlation before run the regression. So these three, you can. Okay, so Y is here. You can see the correlation between price and the sales is negative. It makes sense. If you increase your price, the sale will go down. Okay, and if you increase your advertisement expenditure, you will increase your sale. And it's very consistent. Huh? The correlation between these two are zero. There is no correlation between these two independent variables. Okay, then we are going to run the regression. Previously we run the two-way ANOVA. Now we go into run a regression. Well, how come? How come? Regression. Two independent variables. If there are more than one independent variable, you need to check the convenience. Okay. And then we use enter. The R square is 85%. Oh, I forgot plot the residual. You can say save some of them, but I'm not going to, unless something going wrong. Okay, check it. Is any variable beyond the? It's okay. So we don't need to save any residual because most of the residual is within positive and negative too. It's okay. And the model Haskell 85%. 85% is not too bad. Because you can see. This is many. Okay, you can see the model. The cell will equal plus, oh, it's negative. It's negative. It's negative because you increase your price, you reduce your sale. It's negative. Plus price plus advertisement expenditure. Okay. It seems the model is okay. If I run this model, here we have a x1, y, and we have x2. It seems like it's, so we have an interaction. Okay, so right now I'm going to add this interaction or modeling. Okay, interaction. Oh, okay. Mean center, but I before I do mean center, I just get the interaction between price and advertisement. So this one equal this one multiplied by this one. I didn't do mean center. Actually, I should. Okay, but I won't show you. If I don't do